Hey there, science fans. Welcome to another electrifying episode where we uncover the mysteries of the universe. Ever wonder what's going on when you flip a light switch or charge your phone? It's more fascinating than you might think. It's all about electricity, the flow of tiny particles called electrons. These electrons are the building blocks of the energy that powers our daily lives. These little guys are what make our world go round, powering everything from our homes to our gadgets. Imagine a day without electricity, no lights, no internet, no smartphones. Electricity is like a superhighway of energy, zipping around at the speed of light. It's an invisible force that connects us all, lighting up cities and enabling modern technology. It's a fundamental force of nature, just like gravity, but instead of pulling things together, it can attract and repel. This dual nature makes it incredibly versatile and powerful. Understanding electricity might seem like a tall order, but trust me, it's not as complicated as you think. With a little curiosity and some basic knowledge, anyone can grasp the essentials. We're going to break it down into bite-sized pieces so you can wrap your brain around this electrifying force. From how circuits work to the role of conductors and insulators, we'll cover it all. Get ready to be energized because we're diving into the exciting world of electricity. Whether you're a budding scientist or just curious, this journey will spark your interest and illuminate your understanding. Now we got to talk about electrons. These little dudes are negatively charged particles that zoom around the nucleus of an atom. Think of them like hyperactive bees buzzing around a hive. When electrons get moving in a specific direction, we get what's called electric current. It's like a river of electrons flowing through a wire. The more electrons that are moving, the stronger the current. We measure current in units called amperes, or amps for short. Just remember, higher amps mean more electrons are on the move, which means more power. Now you might be wondering what makes these electrons want to move in the first place. Well, that's where voltage comes in. Voltage is like the driving force behind electric current. It's the pressure that pushes those electrons to get moving. Think of it like water pressure in a hose. The higher the pressure, the faster the water flows. We measure voltage in units called volts. A higher voltage means a stronger push, which can drive more current through a circuit. It's like having a bigger pump to push more water through those pipes. But hold on, we've mentioned circuits a couple of times now. What exactly are they and how do they fit into all of this? Let's find out. A circuit is simply a closed loop or pathway that allows electricity to flow. Imagine it as a continuous loop, like a racetrack, where the electrons are the racers. Think of it like a racetrack for electrons. These tiny particles zoom around the circuit, carrying energy from one point to another. It needs to be a complete loop for the current to flow continuously. If there's a break anywhere in the circuit, the race stops, and the electrons can't complete their journey. A basic circuit usually includes a power source, like a battery, wires, the track, and a load, something that uses electricity, like a light bulb. The power source is like the starting line of the race. The load, such as a light bulb, is where the energy is used. When the electrons reach the load, they transfer their energy, causing the bulb to light up. The power source provides the voltage, which is the force that pushes the electrons through the wires. Think of voltage as the push that gets the racers moving. This push is essential because it drives the electrons through the circuit, ensuring they reach the load. The wires act as conductors, allowing the current to flow easily. They are like the smooth, well-paved tracks that make the race possible. Conductors are crucial because they provide a path with minimal resistance, ensuring the electrons can move freely. And finally, the load uses the electrical energy to do work, like lighting up a bulb or powering a motor. This is where the energy is put to use. When the electrons reach the load, they transfer their energy, causing the bulb to light up or the motor to run. It's the moment when the race reaches its climax. It's like a chain reaction. The voltage pushes, the current flows, and the load does its thing. Each component plays a vital role in the circuit's operation. The sequence is crucial. Voltage initiates the movement, current carries the energy, and the load utilizes it. Without any one of these elements, the circuit wouldn't function. But what happens when we change the voltage or resistance in a circuit? Adjusting these factors can significantly impact how the circuit behaves. That's where things get really interesting. By tweaking the voltage or resistance, we can control the speed and flow of the electrons, altering the circuit's performance. This is the essence of electrical engineering, where understanding and manipulating these variables can lead to innovative solutions and new technologies. Section 5. Ohm's Law, the traffic cop of electricity. This fundamental principle is essential for anyone delving into the world of electronics and electrical engineering. Now, to understand how voltage, current, and resistance all relate to each other, we need to talk about Ohm's Law. This law is the cornerstone of electrical theory, providing a clear and concise way to predict how electrical circuits will behave. Don't worry, it's not as scary as it sounds. Once you grasp the basics, you'll find it quite intuitive and incredibly useful for solving a wide range of electrical problems. Ohm's law is a simple equation that describes the relationship between these three electrical quantities. The equation is V equals sine IR, where V stands for voltage, I for current, and R for resistance. This equation is a powerful tool that allows us to calculate any one of these quantities if we know the other two. It states that the current flowing through a conductor is directly proportional to the voltage across it and inversely proportional to the resistance. This means that if you increase the voltage, the current will also increase, provided the resistance remains constant. In simpler terms, this means that if we increase the voltage, we'll increase the current. This is because the electrical pressure pushing the electrons through the circuit is greater, causing more electrons to flow. But if we increase the resistance, we'll decrease the current. It's a balancing act. Higher resistance means it's harder for the current to flow, much like how a narrower road slows down traffic. Ohm's law is like the traffic cop of electricity, making sure everything flows smoothly and safely in our circuits. By understanding and applying this law, we can design and troubleshoot electrical systems with confidence, ensuring they operate efficiently and effectively. Section 6. Conductors, the electricity superhighway. We've talked about circuits and how they provide a path for electricity to flow, but what makes a material a good conductor of electricity? Conductors are materials that allow electric current to flow easily. They have loosely bound electrons that can move freely from one atom to another. Metals like copper, silver, and aluminum are excellent conductors, which is why we use them for electrical wiring. Water is also a good conductor, but only when it contains dissolved salts or impurities. Think of conductors like a superhighway for electrons. They provide a smooth and easy path for the current to flow. Section 7. Insulators, stopping the flow. On the other hand, insulators are materials that resist the flow of electric current. They have tightly bound electrons that are not free to move around. Rubber, glass, plastic, and air are all good insulators. That's why electrical wires are coated in rubber or plastic, to prevent the current from flowing where we don't want it to. Insulators are like roadblocks for electrons. They prevent the current from taking a detour and keep it flowing safely along the intended path. Section 8, direct current, DC, one-way street for electrons. Now, let's talk about the different types of electric current. The first one we'll cover is direct current, or DC for short. DC is a type of current that flows in only one direction. It's like a one-way street for electrons. Batteries, solar panels, and fuel cells all produce DC. DC is used in many electronic devices like smartphones, laptops, and LED lights. It's a steady and reliable source of power for these devices. Section 9, alternating current, AC, the Electron Shuffle. The other type of current is alternating current, or AC. Unlike DC, AC changes direction periodically, flowing back and forth. AC is generated by power plants and is what we get from our wall outlets. It's used to power most household appliances and industrial equipment. The advantage of AC is that it can be transmitted over long distances with minimal energy loss. That's why it's the preferred method for distributing electricity over power grids. Section 10. Electricity powering our world. As we've learned, electricity is a fundamental force of nature that plays a vital role in our daily lives. From powering our homes and businesses to enabling technological advancements, electricity has revolutionized the way we live, work, and interact with the world around us. Understanding the basics of electricity is essential for anyone who wants to navigate our increasingly technology-driven society. It empowers us to make informed decisions about our energy consumption, troubleshoot electrical problems, and appreciate the wonders of the invisible force that shapes our modern world. Section 11. Stay curious about current. So there you have it, a crash course on the basics of electricity. We've covered everything from electrons and circuits to conductors and insulators. Remember, electricity is a powerful force that can be both beneficial and dangerous. Always treat it with respect and follow safety guidelines when working with electrical equipment. And most importantly, never stop asking questions and exploring the world around you. There's always more to learn, especially when it comes to the fascinating world of science. Stay curious.